Welcome back to my channel. Today we're going to be talking about linear partial fraction decomposition. Before we get into the actual partial fraction decomposition, we're going to talk about simplifying fractions. So we are given this problem here, 2 over x minus 3 plus negative 1 over x plus 2. So in order to add these fractions, the first thing that we need to do is get common denominators. The fastest way to get a common denominator is to multiply that fraction by the other's denominator. And so we have 2 over x minus 3 plus negative 1 over x plus 2. So to get common denominators, I'm going to multiply my first fraction by x plus 2. And if I do it to the top, then I need to do it to the bottom. And I'm going to multiply the second derivative by x minus 3 over x minus 3. Actually multiplying out the bottom or the denominator isn't necessarily something that we absolutely have to do. So when I am adding these together, I'm going to have an x plus 2 times x minus 3 in parentheses and the same thing over here. So no matter what I have in the numerator, I now have a common denominator. So we're going to multiply these out. So 2 times x plus 2, so we have 2x plus 4. Negative 1 times x minus 3, so I have negative x plus 3. So get common denominators, we need to multiply it out. Now we're going to actually do the operation, so we're going to do that addition. So when I add these together, our common denominator, we just have the 1. So I have x plus 2 times x minus 3. So now we're going to add those numerators together. So we have a 2x, a plus 4, plus negative x plus 3, and then we are going to simplify. So our simplifying is just combining like terms. So 2x minus x is going to give us x. 4 plus 3 is 7, so we have x plus 7. We might get something like this. The only other way we might write it is if we were to multiply out the denominator. If we do, we're going to get x squared. We have 2 times x and a negative 3 times x, so that difference would be a minus x and then a minus 6. So when I get two fractions and I need to combine them together when they don't have common denominators, we're going to go through this process. We're going to be learning about partial fraction decomposition, which is going to be working our way backwards from getting those common denominators. So we want to get an end goal of what we started with here. So there's a few things that we kind of need to know. There's two cases when we talk about partial fraction decomposition. The first, the degree of the top is less than the degree of the bottom. If we look at what we just have, this final equation here, the degree of the top is 1, the degree of the bottom is 2, so the degree of the top is less than the degree of the bottom. And this would be our first case. This would be called a proper partial fraction decomposition. On the other hand, we have an improper, and that's when our degree of the top is bigger or equal to, so greater than or equal to, the degree of the bottom. And that just means we might have to do a little bit more work before we actually do the problem. One of the really nice things is that AP focuses on non-repeating linear factors, so we are going to be focusing on non-repeating linear factors. Okay. So the thing that we need to know is that partial fraction decomposition kind of consists of two equations being divided by each other. So we have f of x divided by g of x. F of x divided by g of x is equal to these other two fractions here that we're going to be adding together. A lot of times we use big A and big A and big B on the top, and then the bottom we want linear factors, so we have something times x plus or minus a coefficient, and these are not going to be the same. And I know they're not going to be the same because they're non-repeating linear factors. So we use different variables to kind of show that. So the one stipulation where g of x has to be those two denominators multiplied together. So ax plus b times cx plus d. So we're going to figure out a way called partial fraction decomposition to take a fraction that is not simplified and use it to do some simplification, because eventually we're going to want to do some integrals. And when I try to take the integral of something like x plus 7 divided by x squared minus x minus 6, I can't take the derivative as is because our u substitution wouldn't quite work. So we use partial fraction decomposition to kind of get around it. So we did this problem but backwards, so we're going to look at the process of partial fraction decomposition here to kind of help us out. So the first thing that we're going to do with partial fraction decomposition is we are going to factor the denominator. So when I am looking at our problem here, step 1, factor the denominator. So because we have this problem out front, I know that the top is still going to be x plus 7. The bottom, we have x plus 2, x minus 3. It multiplies to negative 6, adds to negative 1. So I know that this is going to be good. We can go ahead and set up our equation. So we have x plus 7 over those factors, x plus 2, x minus 3, equals. We want to set up our fractions so that way one of them is going to be x plus 2 and the other one is going to be x minus 3. What we don't know is what goes in the top, so we need to put a variable there. So we factored the denominator, we set up our equation. So now what we're going to do is we are going to multiply both sides by the denominator of our original. So that denominator of x plus 2 times x minus 3. Some space, so I'm going to write it out. So we're multiplying both sides by x plus 2, x minus 3. And I'm going to do that to this side as well. So we are multiplying by the original denominator. Okay, when we do this, if I am multiplying by the denominator, that means I'm doing the inverse operation here. So x minus 3 goes away, x plus 2 goes away, leaving this side as just x plus 7. So x plus 7 is equal to this x plus 2 and x minus 3 goes to each the first fraction and the second fraction. So if I x plus 2 times a over x plus 2, those x plus 2's are going to go away. So I still have a, but then we multiply it by an x minus 3, so I have a times x minus 3. This is being added to, I have x minus 3 times b over x minus 3. Those cancel each other out, they make a special form of 1, and I'm multiplying it by x plus 2. So all we did was simplify what we have. So we get this here where we have no fractions now. So we have x plus 7 is equal to a times x plus 2 and plus b times x minus 3. This is the really big piece that we want here. So we've gotten rid of our fractions. We're now looking at just the numerators, but we need the numerators as a constant multiplied by something to kind of help us out. So what we want to do now is we need to plug in some number for x. And hopefully that number is a number that we can kind of deal with and make it easy to solve for a or b. I can technically choose any number that I want. Some numbers that we choose are going to make it a little bit harder, meaning we might need a system of equations to then solve for a and b. Other numbers that we can pick can make things a lot easier for us. Those numbers are going to be the zeros of our denominator. So if we can find the zeros of the denominator, we can make this a lot easier. So we're going to take the two factors from the denominator originally, x minus 3, x plus 2, and we are going to set both of those equal to 0. So we have x plus 2 equals 0, x minus 3 equals 0. This is going to give me x is equal to negative 2 and x is equal to 3. So we are going to take a second and we are going to plug these values in. So these are the numbers that we're going to plug in. We're going to plug in x equals negative 2. We're going to plug in x equals 3. So we're going to plug in x equals negative 2 first. So x is equal to negative 2. We are going to plug in negative 2 for every x we see. So the first thing we see is x, so negative 2 plus 7 equals a times negative 2 minus 3 plus b times negative 2 plus 2. Okay, so we have negative 2 plus 7. That's going to give us 5. We have negative 2 minus 3, which would be negative 5. And then we have b times negative 2 plus 2, which is 0. So we have 5 is equal to negative 5a. Well, we have a by itself, so now I can solve for it. So I'm going to divide both sides by a. This is going to give me 5 divided by negative 5. So a is equal to negative 1. We're going to now do the exact same thing, but we're going to plug in 3. So I have 3 plus 7 is equal to a times 3 minus 3 plus b times 3 plus 2. So I have 10 is equal to a times 0 plus b times 5. So 10 is equal to 5b. So 2 is equal to b. So now what we're going to do is we're going to plug these back into our original function. So we now have x plus 7 divided by those factors is equal to. So here's where I want to be a little bit careful. I just want to make sure that I'm plugging it into the right thing. So this first one is a divided by x plus 2. A happens to be negative 1. So I'm going to put negative 1 over x plus 2. And we have x minus 3, 2 over x minus 3. So this is where we rewrite our fractions. And if we look at the front, 2 goes with the x minus 3, negative 1 goes with x plus 2. Ours is just backwards because we wrote the other factor first. So not a big deal, and we get our answer. So one of the things that you may be looking at here is just the amount of stuff that we need to do. Once we know what to do, everything can be a little bit streamlined. Once the fractions are gone, now it's just about plugging in numbers that are easy to work with. So if I really wanted to, I could plug in x equals 0. So that would be 7 equals negative 3a plus 2b. But I would need something else because it doesn't get rid of one of my variables. So with partial fraction decomposition, we kind of want to work smarter rather than harder.